When we look out into the night sky, we are looking back in time. The light from distant stars and galaxies has travelled for billions of years to reach us. It carries snapshots of the universe as it was long ago. For a long time, the very earliest moments after the Big Bang remained hidden. Those first few 100 million years were shrouded in a fog of neutral hydrogen. The first galaxies were faint and difficult to detect. Now the James Webb Space Telescope lets us peer through that fog and see farther than ever before. JWST is built to capture infrared light, that is the stretched out glow from those ancient distant objects. It is revealing galaxies from when the universe was just a tiny fraction of its current age. In this video, we will explore the deepest views JWST has captured so far. We will focus on the latest confirmations from 2026, galaxies seen as they existed only 280 million years after the Big Bang. These are among the earliest structures we know of. They are challenging what we thought we understood about how quickly the cosmos began to organize itself. Let us start by looking at how we even measure these immense distances and why each new record matters. To understand these very distant galaxies, we first need to understand how we measure their distance in time and space. The universe is expanding. As light travels toward us from far away, that expansion stretches the light waves. Shorter wavelengths like ultraviolet light or blue light from hot young stars get shifted toward longer, redder wavelengths. We call this redshift. Redshift is our ruler for cosmic history. A small redshift means the light left a galaxy relatively recently. A large redshift means it left a long time ago, when the universe was much smaller and younger. Astronomers use a number called Z to describe redshift. For example, a galaxy at Z equals 1 has light stretched by a factor of 2. The age of the universe when that light was emitted is roughly half what it is today. JWST works in infrared because the light from the earliest galaxies has been stretched so much that it arrives as infrared now. Higher Z means earlier in time. Galaxies at Z greater than 10 existed when the universe was less than about 500 million years old. The ones we are focusing on here push beyond Z equals 13 or 14. Taking us back to around 280 to 330 million years after the Big Bang. Spectroscopy is the key to confirmation. While images give us photometric estimates of redshift based on colors, a spectrum shows sharp features like the Lyman alpha break or emission lines. Those let us pin down the exact Z value and prove the galaxy is truly that distant. In the upcoming chapters, we will look at how JWST finds these objects in deep fields and what the latest 2026 confirmation tells us. To find these extremely distant galaxies, JWST uses a strategy that has worked well for decades in astronomy. It takes very long exposures of small patches of sky that look almost empty at first glance. These are called deep fields. By staring at the same region for hours or even days, the telescope collects enough faint light to reveal objects that would otherwise be invisible. In infrared, where JWST excels, this reveals galaxies whose light has taken billions of years to reach us. Several major surveys lead the search for the earliest galaxies. One is JADES, the JWST Advanced Deep Extragalactic Survey. It combines wide area imaging with targeted spectroscopy in fields like Goods South. Another key area is the Cosmos field, which provides a larger canvas to find rare, bright examples at extreme distances. Astronomers first use NIRCam to take multi-filter images. These create color pictures that help identify candidates based on their redshift signatures. A galaxy at very high redshift drops out of shorter wavelength filters because its light is stretched far into the infrared. That dropout pattern flags potential record breakers. Then comes the crucial step. NIRSpec takes detailed spectra of those candidates. The spectrum reveals exact redshift by showing where key features like the Lyman break or emission lines appear. Only spectroscopy gives us true confirmation that a galaxy is as distant as it seems. In 2026, this approach paid off dramatically in the cosmos field. Teams targeted promising candidates and confirmed galaxies at redshifts beyond 14. We will look at one standout example next. Before 2026, JWST had already set impressive records for the most distant galaxies we could confirm. One early standout comes from JADE survey. In late 2023 and early 2024, astronomers identified JADE's GS-Z13-0 at a redshift of about 13.2. That placed it roughly 325 million years after the Big Bang. Spectroscopy confirmed the distance, and the galaxy appeared surprisingly bright for such an early time. Then in mid-2024, the same JADES team pushed further. They confirmed JADE's GS-Z14-0 at a redshift of 14.32. This galaxy existed less than 300 million years after the Big Bang. It was larger and more luminous than models had predicted. That finding started to hint that the galaxy formation in the early universe might have happened faster than we expected. These discoveries built on photometric candidates from deep imaging. Teams used dropout techniques in NIRCam data to spot potential high redshift objects, then followed up with near-spec spectra for solid confirmation. By the end of 2025, a few other candidates hovered around Z greater than 14, but none had full spectroscopic proof beyond the JADES examples. The frontier was about 290 to 300 million years post-Big Bang. In 2026, that boundary moved again. A new spectroscopic confirmation in the cosmos field took us to redshift 14.44 at an even earlier epoch. This is the breakthrough we turn to next. On January 28, 2026, astronomers announced a new record. Using JWST data, they confirmed the most distant galaxy yet seen with full spectroscopy. The galaxy is called MOM-Z14. It sits in the cosmos field, a large deep survey area. NIRCam imaging first flagged it as a promising candidate. Then NIRSpec captured its spectrum, revealing a sharp Lyman break and several rest UV emission lines. Those features pin the redshift at 14.44, plus or minus a small uncertainty. That redshift corresponds to light emitted when the universe was only about 280 million years old. We are seeing MOM-Z14 as it was just 2% of the way through cosmic history. This pushes the observational frontier beyond previous records. Like JADE's GS-Z14-0 at redshift 14.32. MOM-Z14 now holds the title of the most distant spectroscopically confirmed source. It is not alone in this extreme region. Other teams have continued confirming candidates at redshifts greater than 13 and 14 through ongoing surveys. But MOM-Z14 stands out as the farthest so far. What makes these galaxies especially interesting is not just their distance, it is their properties up close. We will look at those surprising traits next. What stands out most about these galaxies we are seeing at such early times is how unexpected many of their properties are. First, they are remarkably luminous. MOM-Z14, for example, shines with a brightness in the ultraviolet that places it among the brightest sources ever seen at any distance. Models before JWST predicted far fewer such bright galaxies this soon after the Big Bang. Yet here we have one, and it is not unique. Others in this early population show similar high luminosities, about 100 times more abundant than theory suggested. Second, these galaxies are extremely compact. MOM-Z14 has a circularized radius of only around 74 parsecs, or roughly 240 light-years across. That is hundreds of times smaller than our Milky Way, yet it produces comparable ultraviolet light output in a tiny volume. The light is concentrated, suggesting intense, rapid star formation packed into a small space. The spectrum tells us more. The steep ultraviolet slope indicates very little dust attenuation and a young stellar population dominating the light. We see rest UV emission lines, including features from nitrogen, with ratios that are highly supersolar. The nitrogen to carbon abundance hints at patterns seen in local globular clusters, which may have hosted luminous supermassive stars in the past. This could connect directly to how the earliest heavy elements formed and spread. Overall, these traits point to galaxies assembling and evolving much faster than expected. The data show bright, compact, chemically enriched systems emerging in the first few 100 million years. These early galaxies carry important clues about two big processes in the cosmic history: reionization and the formation of the first structures. Reionization is the period when ultraviolet light from the first stars and galaxies began to clear the neutral hydrogen fog that filled the young universe. For JWST, models generally predicted that the intergalactic medium would remain almost entirely neutral at redshifts around 14. That means strong absorption, known as damping wing, should appear in the spectrum of any distant source. Yet the spectrum of MOM-Z14 shows only a weak damping wing. This suggests that the space immediately around the galaxy was already partially ionized. The intense light from its young, massive stars likely created a bubble of ionized hydrogen, perhaps extending tens of thousands of light years. At this redshift, where models expect a neutral fraction near 100%, finding even local ionization is noteworthy. It provides a direct hint that reionization may have started earlier in some regions, or advanced more quickly than expected, driven by these luminous early galaxies. On a broader scale, the abundance of such bright, compact galaxies helps explain how structure began to form so soon after the Big Bang. These sources produce enough ionizing photons to contribute meaningfully to clearing the fog over larger volumes as more of them appear. Their rapid assembly and chemical enrichment also tie into how the first heavy elements spread, setting the stage for later generations of stars. At the same time, the data highlight tensions with standard models. Pre-JWST predictions underestimated the number of bright galaxies this early by factors of 100 or more in some surveys. This requires rethinking aspects of galaxy formation timelines, star formation efficiency, or perhaps the initial mass function of stars. The observations do not overturn cosmology, but they push us to refine our understanding of how quickly the universe organized itself. The lambda cold dark matter model still holds up well on large scales. What we are seeing is pressure on the details of how galaxies form and evolve in the very early universe. Astronomers are already working on updated simulations and revised assumptions to better match the observations. Looking at these images and spectra from JWST, it is hard not to feel a quiet sense of awe. The telescope keeps delivering views we could only imagine a few years ago. Each new deep exposure and each confirmed spectrum adds another piece to the puzzle of how the universe got started. The surprises keep coming, and they remind us that our picture of the cosmic dawn is still taking shape. What excites me most is not just the records broken, but how they open up new questions. We get to watch science unfold in real time. Observations challenging ideas, people refining models, and everyone learning together. JWST was designed to explore this frontier, and it is doing exactly that. There will be more fields to image, more candidates to follow up, more insights waiting in the data. For now though, it is enough to sit with the fact that we can see this far back. The universe is vast and full of unexpected beauty. Exploring it one quiet revelation at a time is what keeps the curiosity alive. Thank you for watching. If any of this sparked your interest, there is always more out there to discover. Sláinte.